Will you accept pictures of the homework for ICA?
I do.
Yeah.
On the ICAs, I generally prefer it as a PDF, mostly because then if it's a JPEG or a picture, I have to download it as a separate file and open it on my computer. But PDFs, the auto grader on Canvas will just open it up for me.
Okay.
So especially if it's multiple pages, I prefer PDF, but I'm not going to mark you down if you send JPEGs.
Right. Okay.
If it's one that, if it's in a, there's some assignments where it really makes a difference for me when it comes to grading, those I'll be picky about and say you have to be PDF.
Okay.
But for the most part, if it's letting you submit a JPEG, I'm okay with you turning in a JPEG.
Sounds good. Yeah, just because I put quiz homework or the quiz work on the back side of my ICA there, so yeah, just get your pictures of that.
It's funny, like Spanish. Yeah. I'll show it $3,000. I think for either space is 255.
Hey, Sean, like conversions are harder things to get in this class, but once you get it, the rest of the class becomes easier.
We'll keep using conversions a lot of different places because they will keep showing up. That's why we're spending our time on them now.
Okay.
And understanding how to do word problems based on percentages and conversions and with a little bit of algebra thrown in winds up being really helpful down the road. So, but yes, this is absolutely something that will continue to bother you, but you will continue to get good at. The general theme in most chemistry classes is as soon as you feel comfortable with something, we add a new wrinkle. So you're still going to be fighting with conversions, but they're going to be way trickier conversions, and you'll be struggling with them less than what you're doing now. Because we're just going to keep adding. Yeah, because right now we're laying the foundation now. And when you come back to these problems at the end of the quarter, you're going to look at it and be like, oh man, I was worried about this.
Are you going to do anything with like organic chemistry?
Not till third quarter. We got to get a bunch of stuff out of the way first, and then yeah, third quarter is when we get to a lot more of the more specific subjects, and then that lays foundation for you to go take a second year course in whatever, you know, for engineers. You're not taking organic chemistry next, you're taking let's say mass and energy balances next, and there are some aspects of this class that will show up there, but it'll be different things that show up for bio majors that are taking OChem next.
Okay.
So we'll get into that stuff. Yeah, the OChem, intro to OChem stuff we'll get into in Chem 103.
Okay, so I got to take Chem 102 first.
You have to take what?
Chem 102?
Yes. Yeah. Although, what's your major? What are you trying to say?
I'm going towards like ecology.
Okay.
Yeah.
So I don't know. So Humboldt State in particular is weird. They don't like our units.
Right.
Because we're quarter system, and somebody in the chemistry department over there has a stick up their butt, and they won't take our units for a lot of things. They always wind up taking our units, but they'll tell you no.
Okay.
And then our articulation officer has to come in and say, no, this is the same class. Look, right here, it says the same things as what you're asking for. So don't take no for an answer from Humboldt in particular.
I don't.
Yeah, their ecology in general is not a major. I don't know how standardized it is between different schools. So it might be something where
I've done all the research and the transfer.
So you only need one quarter of OChem?
I need to do these 3 quarters, Chem 1, Chem 2, and Chem 3, and then that'll be one class of chemistry over there.
Well, we offer, is it OChem or is it something else?
It's not OChem specifically. I was just interested in that.
So that is the sort of thing that they would tell our students, like, no, our OChem class is as good as their OChem class. So if it is OChem, then you can take it here, but you don't have to. You clearly don't have to. But
yeah, it may or may not transfer.
Yeah, it'll transfer. They'll just fight it for a second.
Okay.
Our OChem series transfers anywhere in the CSUs or UCs for full upper division OChem. There are some of them where it gets a little bit weird because some of the UCs have OChem listed as an upper division, which is 300 or 400 level. And the policy is to not accept 300 or 400 level classes from community colleges. But there's a workaround that we can do with that, where they basically, you get credit, you don't have to take the classes again, and our classes transfer as elective, but the net result is you don't have to take OChem once you get there.
Yeah, it's already done for. Cool.
So that applies for anybody. Anybody whose major requires OChem, our OChem series that we offer here transfers anywhere in California, or to CSUs and UCs, for major prep OChem, for bio major, chem major, anything that requires OChem, our OChem series transfers for that. So if it doesn't look like it matches up exactly, talk to me and or the other school, and we'll make sure it works. And then while we're still waiting on people getting back, just thought I would go through the Canvas shell. Anybody who's looking for a copy of the conversion sheet or a printable periodic table, you go down to resources. So underneath the course schedule to the resources link, it's got links to Zoom and stuff like this. A lot of this is still left over from when it was online last year, but the printable resources, here's your official equation sheet for the final exam and the midterms, the same sheet that'll be on both, and the official periodic table for both. It's black and white. There are some other ones you can print that are color if you have a color printer. If you have a big printer, these detailed ones may or may not be legible on your printer because they have a lot of detail on them. But you can still download them. Oh, don't do that. Open with. I'm not going to go through that right now, but that'll work. They are detailed enough that on a regular printer you might not be able to see everything, because it has a lot of stuff that we'll get into what all of this means down the road. The simple one is just going to be your basic, so the simple one in black and white. Oh, that's saved as a ping. That's convenient. It just looks like this. Pretty easy to read from a fair ways away. This is the copy that will be on the exams, that will be printed for you on the exam. So it's a good one to have so you know where everything is. And you're not relying on something that you won't have in a timed situation. And so it's good to get used to the tools you're going to have on the test, rather than have some equation sheet you made yourself that has everything, but you're not going to be able to use on the test. That's not a good habit to be in, to practice from that. You want practice from this and the equation sheet that you're going to have, even if you take notes on it, because if you take notes on it and it's the same setup and same format, visually your brain will still be able to remember, like, oh wait, no, I had this written over here. Or, oh, I circled these three on my, if you used to practice and you have these all called out on the one that you have at home. And, okay, well, why did I have those? And you might have to go back and think about it when you get to the test, but at the very least, you're used to studying from the same piece of paper, same setup. So I highly recommend using the ones that I'm going to give you on the test, not because I think mine are better than anybody else's, but because it's the one that I'm going to give you on the test. The other thing I was going to go over here is that when you want feedback on your quizzes, if you go to quizzes, if you click on your assignments, you can see your attempt here and you can see the grades. I think the other place that you can see this is if you go to grades. So I just filled in a test for one of the test students. So if you go to grades and you click on the assignment, it'll give you what you submitted and a bunch of information, and yours will not be quite so cramped. But it'll say, okay, well, I got 2 out of 2 points there, or I got 3.25 out of 4 points there. So you get the feedback there. I don't always leave comments with the answers, especially if it's something that we're going to go over in class. But you can at least see where I gave you points and didn't give you points. And nope. So like this is just the test student. It's not somebody's actual grade. So I would not usually just respond with nope, although occasionally if you should know better. And but so actually in the kind of thing that I would do, and I did see this once on the conversions, is somebody mixed up centimeters and meters. Somebody wrote a conversion that said that 10 to the minus 2 meters is no, it's the other way around. It's 10 to the minus 2 centimeters is 1 meter. So that's saying that 1 meter is less than 1 centimeter. It's the right multiplier, but it's in the wrong spot. The 10 to the minus 2 should be on bottom, not top. This is the equivalent of writing 100 meters equals 1 cm. Easy to do when you're doing these conversions and you're trying to do them fast, but we all know that that's not true, right? Intuitively, you guys know it's backwards. So if I see a conversion like that, I might circle it and just write no. Right, so usually I'm just drawing your attention. If I'm making a really, really short comment like that, I'm just drawing your attention to something that you know better.
Something that's obvious.
Something that's obvious once you look at it.
Yeah.
But so you won't have the correct answers though on Canvas, we would actually still have to ask you for that.
Right, and we'll go over them in class. Sometimes I will. So like I said, the auto grader on Canvas is awful. If I have you put in your question answers and it's going to be auto graded, then basically I have to guess every possible way that you could write the correct answer, including down to spaces and writing the units properly and improperly. Like if somebody's wrote their answer as 925 kilometers without a space versus 925 kilometers with a space versus putting a space between the K and the M, I have to write those all in separately into the auto grader. So usually if I do it like this and using the auto grader, I'll just put it in once. And as long as you're not, as long as you got the right number and your units are there, you'll get credit when I go back through and do it. But yeah, I always fight with the auto grader in Canvas, and a lot of times I wind up not using it all because it just makes you guys all very, very nervous because you got the right answer, but you got 0 points. And after the 1,000th email I've responded to about, I got the right answer, but it gave me 0 points. I just stopped using it. So yes, I won't always have the right answers in Canvas, but I'm always going to go over the answers in class. And then anything you ask the question is your question 4 or your last question. Especially if it's not something that I'm going to bring up in front of the whole class, I try to respond to all of them, and this is where you will see those responses. So this one was just the test, just as comment response, but usually over here I would have some answer to whatever you asked about. Especially if it's relevant to the class or understanding specific things, I'll either say in class, meaning we'll talk about it here, or I will try to give you a fairly detailed explanation to answer your question, which is one of the reasons why it can take me a long time to grade things, because you guys ask a lot of good questions. And so just as a tour of Canvas, that's how you get to your feedback on these quizzes. And again, I don't go through on the ICAs and the labs and give as much feedback as I do on the quizzes. Usually, especially since I'm grading on a variety of different, some of them are paper, some of them are digital, etc. If you want detailed feedback on the ICAs and the labs, ask me what you did wrong or ask me to go through a problem. Okay? All right, let's go back here. Not there, although we'll leave this up because we might need it in a minute. All right, let's talk a little bit about history. It doesn't seem like it's history right off the bat, but this is a really famous thought experiment from back in the ancient Greek times, so about 2000, 3000 BC, Aristotle era. And they basically came up with this thought experiment that says, well, what happens if you cut a piece of copper in half? And then you take that half and you cut it in half. And you take those halves and you cut it in half. And you keep cutting things in half, and half, and half, infinitely. So the two options are either you get to the point where you can't cut it any smaller, or you could keep going until the copper was infinitely small. Really only two options, right? It has to be one of those two. Aristotle believed that matter can be infinitely small and is made up of 4 primary elements in varying amounts. So copper has some earth mixed in with some fire and some water and some air in a certain ratio, and that's what makes it copper. But you could go infinitely small with it. His rival at the time was a guy named Democritus. And Democritus basically had the opposite approach. Matter is made up of small invisible particles. One of the few quotes from Democritus was, "Nothing exists but atoms and empty space, all else is opinion." We only have a very few things of Democritus's writing. So for starters, this wasn't really science at this point. Because they didn't have the scientific method. They didn't understand why it wasn't science. But basically, they didn't have anything they could test here. There was no testable hypothesis in here.
I'm just curious.
They were curious. They're like, well, these are two options. Let's argue about it.
They were natural philosophers.
Exactly. That's where the original term and why they call it Doctor of Philosophy for PhD for everything now comes from the fact that they were called natural philosophers before the scientific method had ever been, not before it existed, but before it had ever been written down by the Persians in the Middle Ages. So they weren't really doing science. And the other thing that changed things here is that Aristotle was really, really popular. Aristotle was Plato's protege, Plato and Socrates, or Socrates, as he's known. Any Bill and Ted fans? I love Bill and Ted. So Aristotle was he was the golden child. Everybody loved Aristotle. Everybody still knows Aristotle because he did so much stuff with math. And a lot of the early science that we know, it wasn't discovered using the scientific method, but was done by Aristotle. So he was really, really popular, and the other thing that mattered is that he outlived Democritus. They just sent nasty letters to each other and argued with each other for, better part of a decade until Democritus died. At which point Aristotle went to Democritus's city and had all of his writings burned.
Yeesh.
So Aristotle's not a super friendly guy, or at least Democritus said something that really got under his skin at some point. I don't know exactly why they hated each other so much, but they did. So this is, like I said, we really don't know much about Democritus beyond this quote and the fact that he was Aristotle's enemy.
Were you calling them atoms 5,000 years ago?
They were, because an atom actually means in Greek indivisible. So basically he was just saying that you have these, once you get to the small enough pieces, you can't cut them in half anymore. So what do you call them? You call them something you can't cut in half, indivisible, which translates to atoms. So basically this got forgotten for the next several thousand years. Aristotle won, burned all of Democritus's writings. It wasn't until the Enlightenment era in post-Renaissance in Europe and in America that they revisited some of these ideas. And so these three guys in particular wind up being really important. Lavoisier came up with the law of conservation of mass. In other words, no matter what changes something goes through, you have the same mass before and after. Proust, which is not, I don't think it's the same Proust that was the Enlightenment era author. I think it's a different Proust. Had the law of definite proportions, which said basically that for a given compound, you always wound up with the same ratio of, say, oxygen to hydrogen, or nitrogen to oxygen. He said, okay, well, for every time we take a sample of water, we get the same ratio of masses. So if you took water, for instance, you might wind up with, for every 16 grams of oxygen, you wound up with 2 grams of hydrogen when you break it apart into its elements. So
That's one
when
molecule.
you put that, that's, well, they don't know that yet.
But what you wrote on the board is just one molecule of water, H2O.
Close, yes. 1 mole. We'll see what a mole is in a second.
Okay.
So Dalton was the one who took this and put it together and turned it into the idea of atoms and molecules. So Dalton said, well, if you take these two things, all mass is conserved and you have to combine things in these certain ratios. Dalton was the one that realized that the ratios are always whole number ratios relative to each other. So another compound that they knew of at the time, they didn't name it the same thing as us, was wound up breaking down to be 8 grams of oxygen for every 2 grams of hydrogen. So what Dalton did was he came and he realized that 6 is twice 8. For all of these different compounds, that doesn't seem like it's that impressive when I read it like that. But for all of these different compounds, he found out that, okay, well, if it's a nitrogen and oxygen compound, this nitrogen compound has twice as much nitrogen as this other nitrogen compound. And he found that it was always a whole number ratio. So what that told them, where Dalton was able to make a connection here, was what he called atomic theory. Basically, he was able to come up with, from those 3 laws, he came up with the idea that each element is comprised of tiny indestructible particles called atoms. So this is Enlightenment era. They were really, really good at going back and reading everything. They were educated classically, meaning that they were taught everything the Greeks and Romans had ever written, basically. So they'd heard of Democritus, even if it wasn't a widespread idea and nobody really knew what an atom was. So he came back and he revived Democritus's term, an atom. Oh, maybe Democritus was onto something. He couldn't test it, but they used the same ideas. So, and then step 2 is all atoms of a given element have the same mass and other properties that distinguish them from other elements. So in other words, every atom is identical. Every atom of a specific element is identical to every other atom of that element. And these atoms combine in simple whole number ratios to form compounds. So taking two hydrogen atoms and 1 oxygen atom, putting that together is how you get H2O. If you take 2 hydrogens and 2 oxygens, you get a different compound. H2O2, which is hydrogen peroxide. Right, so combining these in whole number ratios to make different compounds. And then 4 is atoms cannot change from one element to another. They can only change how they are attached to other atoms. So this is back in the, I'd say, late 1700s. So this was a long time ago. Didn't have a whole lot of technology by our standards by which to test these things. Seems like quite a leap based on those 3 laws that we had before. Those were scientific laws because they just described the way things behave. This is a theory because it explains why those laws exist.
It's a theory that they couldn't prove back then.
They could in the 1700s.
Oh, okay.
So remember that a scientific theory doesn't mean that it's less well supported. It just means that it explains why other things happen. And a law just explains what happens. Right? So it's an atomic theory because it's explaining why the law of conservation of mass is the way it is. Knowing what you know now, are there any problems knowing what people in our day and age know? I'm trying not to assume that you guys know anything, but at the same time, I know that you know a lot of things about science, whether you realize it or not. Do you see any problems with these 4 postulates? Anything that's not accurate?
4 maybe.
Number 4?
4. Yeah.
Yeah.
He sounds confident to go with 4.
You know, you can, it depends on how you describe things, but yeah, we can actually get some elements to change from one element to another element with enough energy.
The easiest ones are the radioactive ones. All
Exactly.
you have to do is wait.
Exactly. So if anything radioactive is any nuclear reactions, actually is changing things from one element to another element. But in the 1700s, radioactivity was unknown. So radioactivity, when it first became known, basically added an amendment here and here, really. Those atoms aren't indestructible. They can be broken apart and turned into other atoms. But it's sort of the exception to the way things normally work. So it's an adjustment to this atomic theory. It doesn't mean we throw out the atomic theory.
Like, when was Dalton versus when was Marie Curie?
So Dalton being late 1700s, Marie Curie was late 1800s. So she was about 100 years later. So a little bit more history going on from here. Now that this is here, but before Marie Curie, they come up with this experiment, which is basically, it's a complicated diagram. It's basically a big glass bowl where if you put a really high voltage between a piece of metal here and over here in the anode, we can actually get these tiny little particles to fly through this. We can measure where they go, and they're affected by magnetic fields. We know that they knew that they traveled in straight lines, they had a negative charge, and they were 2,000 times smaller by mass than hydrogen. Well, hydrogen's the smallest element. And going back here for a second, if each element is comprised of tiny indestructible particles called atoms, there shouldn't be anything smaller than the smallest element. So this right away starts poking holes a little bit before we even get to nuclear reactions, because they also notice that they're identical no matter what materials are used. You could mix up what the anode and the cathode were. As long as you applied enough voltage, you could get the same types of particles to come out. And so what that meant is that the atoms themselves are made up of smaller pieces. So they're not indestructible, they're not indivisible, they're not the very smallest piece of matter because we found something smaller. So they called these cathode rays, which is where we still get the name for CRTs. CRT monitors, the big bulky ones that you put a magnet on top of would change the color. Those are actually this exact setup, except that they're firing those cathode rays and using them to light up a pixel on your screen. Right? It's what old TVs are. So those are cathode ray tubes is what CRT stands for. And so they went and they started trying to figure out exactly what this was, what these smaller building blocks might be. So they came up with an experiment called Millikan oil drop. Millikan came up with this setup where he basically said, okay, I can make these really, really, really small droplets of oil. And then I can fire X-rays at them. And if I fire X-rays at them, sometimes they wind up with a charge when you fire X-rays at these oil droplets. And you could change, if you varied the charge between these two plates on top and bottom, you could get these tiny little oil droplets to float. When the force of the magnetic field pushing against those charges was equal to the force of gravity pulling them down, you could get them to hover, basically. And what he found is that the charge on each of those oil droplets, in order to get it to float, they could measure the charge directly. And he found that the charge was always a whole number ratio of each other. 16 times 10 to the minus 19 coulombs, or 3.2 times 10 to the minus 19, which is double that. Or 4.8 times 10 to the minus 19, which is triple that. We have another whole number situation happening, where things are only happening in whole number ratios. So this was basically the first way they were able to measure the charge of an individual electron. In our terms now, these cathode rays are what we now call electrons. And we can measure the charge with them directly by doing this oil drop experiment. So what's different about this versus ancient Greece is that they had the engineering knowledge to come up with some of these weird experiments, and then had enough knowledge of what was happening to actually make some conclusions based on it.
So so how do you electrically charge something without electricity?
So they understood that electricity existed, because that was Ben Franklin time, right?
Electricity, they just didn't know.
They didn't know why.
Okay.
They knew what a volt was, and they knew that if they hooked up metals with two different metals with wires and allowed ions to transfer back and forth between them, they could make batteries. They called them galvanic cells or voltaic cells. So they knew a little bit about what electricity, how to generate small amounts of electricity. They didn't know everything they could use it for, but they knew how to make these charged plates. They could play around with charges a little bit, and they knew that magnets affected some of this stuff too.
electrons helped us to discover electrons.
And then once they knew electrons were there, they were able to start characterizing the electrons. So we know we have these tiny little particles. We know that they have a negative charge. Well, we better try and measure that charge. So knowing that they existed then laid the groundwork for them to start characterizing and understanding more of what it actually was and how it worked. So what this experiment showed is not only were we able to measure what the charge was, we found that all electrons have the same charge and the same mass. So again, we wind up with a situation where we wind up with these indistinguishable tiny particles that make up everything else. And then we have this next part actually was done all theoretically. If we know that atoms are neutral, because they don't have a charge, but electrons come from atoms and they're negative, what else do we know about atoms then? Just from
They
those,
gotta have a positively charged particle.
you got to have a positive, right? And so what they originally came up with is what's called the plum pudding model, which they basically said the plum pudding model, no matter what they did, they couldn't get a positive electron to come out. They couldn't make anything positive come out of these atoms. So they said, well, we must have a bunch of tiny little negative particles embedded in this larger atom. And this larger atom is made up of stuff that's all positive. But occasionally we can get a negative to fly out of it. So they call this the plum pudding model because they're British and the British don't know how to make desserts. Plum pudding, this is a picture.
Well done.
If you look at what this picture is, this is plum pudding. It's this like really, really weird bready thing with like plums. It's a fruitcake basically.
That's not pudding.
It's British, exactly. They may have invented the language, but they don't use the words right anymore.
Pudding
Yeah,
is
they also put
dessert.
freaking blood in pudding too.
Exactly. We don't want blood pudding either. So, the plum pudding model was so described because this is how they thought of the atoms, and it resembled something that they all knew at that time, since everybody that was working on this was British. Or continental Europe. Essentially, that's what it was. At this time, when all of these discoveries were being made, there was very little science happening in this area in other parts of the world. Some pieces of this had been discovered earlier in other places, but the timeline that we have the most information about is Western Europe. So it's not to say that other cultures didn't know anything about chemistry, but they didn't describe it the same way that our modern framework is built around. So that's why we still have the plum pudding model, and you now know what a plum pudding is because of J.J. Thompson, I think. No, wait, yeah, J.J. Thompson. J.J. Watt is the football player. Yes.
This is science, people.
So the reason that this is worth describing the plum pudding model, it's not accurate. But J.J. Thompson's student, whose name was Rutherford, came up with an experiment that he thought was going to be able to prove the plum pudding model to be accurate. And so he came up with this idea. It's like, okay, well, if I take these alpha particles, which are a form of radiation, they didn't know what radiation was at the time, but they knew that they could make these positively charged particles that were about the size of a helium atom, and they could fire them really, really fast from these radiation sources. Said, okay, well, if we take gold atoms, we pound them out really, really thin, so it's only a couple of atoms thin, we should be able to fire alpha particles at it, and when the positively charged alpha particles hit the plum pudding model, the positive charge from the pudding should slow them down. And you should be able to measure when they come out the other side how much slower they're going, and use that as a way to estimate, what the density was of this plum pudding. But what Rutherford actually saw was not what he expected. Take the gold sample, when he fired alpha particles at it, most of them went straight through, and they hit the other side with the same exact velocity that they left with. But occasionally, a small fraction of them bounced off in really weird angles. So Rutherford set out to prove his mentor's theory correct, plum pudding model was correct, and all he really succeeded in doing is saying, well, that's weird. That doesn't match what I think it should be. Which we'll find is one of the most interesting things to hear in science is not eureka. It's, that's weird. Because it means something isn't behaving the way you expected. Usually that means that you did something wrong with your experiment, but occasionally it means that you found a flaw in the existing scientific theory. So what Rutherford actually discovered was that pretty much all of the mass in an atom is stuck right in the middle, in what's called the nucleus. If these alpha particles managed to go through and not hit a nucleus, they didn't interact with anything. It was just empty space. But if they happened to hit the nucleus, that's where all the positive charge was, as well as the mass. And so they would get bounced off at really weird angles. They were basically all just the same as what you would predict from classical geometry and Newtonian physics. Like bouncing a billiard ball off of a wall, you get really predictable angles when you do that, right? If you fire something really fast here, maybe a pinball is a better analogy, the bumper and pinball. It comes in, hits the bumper, fires off at a different angle, right?
Yeah.
And you can measure where those bumpers, the nuclei, are by looking at the angles that the atoms come off, or that these alpha particles come off. So Rutherford started trying to prove his advisor right and wound up getting an entire chapter in textbooks named after him and a unit named after him because he discovered the nucleus, basically. Or at least he was the first one to describe what we know as a nucleus now. Hard to say discover when it's something that's been around since the beginning of time. But nobody knew what a nucleus was in an atom up to that point. They knew what a nucleus in a cell was, which is why the term gets used, and it's confusing to use it in both places. But he basically said, well, this is a lot like the nucleus in a cell, so I'm going to call it the nucleus. And so the nuclear theory was another amendment to atomic theory. So that most of the atomic mass is concentrated in the nucleus. All of the positive charge is concentrated in the nucleus. The nucleus is made of a discrete number of protons. And then the electrons are spread around the nucleus in a way that balances out the charge. So the reason they were able to say that there's a discrete number of protons is based on that similar to oil drop experiment. They're able to then say, okay, well, if no matter what we use for the atom here, when we take away one electron, we get the same charge. And the difference in charge between the nucleus of a hydrogen atom and a helium atom is the same charge. So they were able to basically say, okay, every element is defined by how many protons it has in its nucleus. And they were always a whole number. You never had a partial number of protons, which is why you don't have element 1.5. You have element 1, which is hydrogen, you have element 2, which is helium, and nothing in between, because each nucleus has a discrete number of protons. Discrete means a whole number, an exact number. Means that it's a counting number, right? You can't have 1/10 of a proton. So all of this started laying framework for the periodic table. The last thing I want to talk about, probably not the last one, I have like 3 whole minutes left. This was another one that they were able to figure out pretty easily from looking at what they already knew. If hydrogen has 1 proton and helium has 2 protons, but helium is 4 times heavier than hydrogen, there has to be something else that has mass. The electrons are too small to make up that difference, and it can't be something that has a charge, or there would be more than a difference of 1 in their protons. So they said, well, there have to be these other particles that we call neutrons. Neutron for neutral. Protons are positive, neutrons are neutral, and electrons are negative. And that's all Benjamin Franklin's fault. Benjamin Franklin came up with the experiment where you take silk and you rub it on glass. And you notice you could build static static charge, static electricity, by doing that. And he just arbitrarily said, well, I don't know what's going on here, but I know there's electrical difference between these two things. So I'm going to call this one negative and this one positive. And as a result, we wind up with things that gain an electron and their charge drops. If he'd switched which one he called positive and negative, then you could gain an electron and your charge would go up the way that it intuitively makes sense. But
That's not his fault, that's our fault. We can
It's-
change it just as easily as we change the.
no, it
inches.
turns out we can't.
We change it just as easily as we could change to the metric system.
Well, okay, yes, that's accurate.
Science.
All right, so
I didn't get that last
to recap, elements are defined by how many protons you have in the nucleus. Ions are defined by the net charge, which is the result of electrons and protons. Extra electrons means a negative charge. If you change the number of protons, you don't change the charge, you change the element.
And then it's an ion at that point.
And then if you didn't also change the electrons, that would also be an ion, yes. So changing protons changes what element you have. Changing how many electrons you have changes the charge on that nucleus, on that atom. And that's what we call an ion. An ion is anything with a charge, positive or negative. And an isotope is defined by the total particles in the nucleus. So if you add extra electrons or you take away electrons, you change the charge. If you add neutrons, you change what isotope you have. And so changing the number of neutrons does not change protons, so you're not changing elements, and it doesn't change the charge. All that's changing is the mass. And so it's still the same element, but it's a little bit heavier. It has extra mass. And so that is one more adjustment that we would have to make all the way back to atomic theory. All atoms of a given element have the same mass and other properties. Not quite.
Not all the way.
Right, so all atoms of a given element have the same number of protons, and changing the number of neutrons changes the isotope, but it's still the same element. All right, so
How would that be done? Changing the, I guess that's.
we'll get into that, yeah.
Later.
All right, so we'll practice using the periodic table and how we can count protons, neutrons, and electrons in class on Thursday, and then we'll go a little bit further. And then next week, we'll get into quantum mechanics. If you can, bring a copy of the periodic table to class on Thursday. It will be helpful.
I was in the lab yesterday forever asking about finding it. Yes.